Hello, everyone. I hope all of you are doing well. My name is Pradeep Kumar Yadav. Today, we are going to talk about a very fascinating, very interesting topic, which is known as rolling motion. Rolling motion is the last topic, as we know, it's the last topic of rotational mechanics, or you can say it for last topic for the whole mechanics also. Yes, of course, there is fluid mechanics, but that is for the fluid bodies. That is discussion for the fluid bodies, basically. So rolling motion is a very important concept. Why? Because during study of this, we will see that all the kinematics and the concept related to dynamics, concept related to energy and rotational mechanics, all the concepts are coming together to be utilized to discuss the rolling motion, right? So that's why it becomes important in the point of view of examiners or in the exam because examiners want such kind of concept where they can ask lots of different concept, right? They can frame different concept in the single question. So that's why it becomes very important. So rolling motion, as I have written here, it is the motion of round objects on a surface. Motion related to the round objects on a surface. Generally, we will take here surface as rough surfaces, right? So first of all, the rolling. Rolling is not a very new term for us. Everyone is well aware about the rolling word, right? In day-to-day life, we generally use this words frequently. Like in the case if you will drag a ball on the road or on the surface, so which kind of motion that ball shows? We know we call that motion is a rolling motion, or you can say we call that the ball is rolling. In this manner, we use this term, right? Or if you will see a vehicle which is moving, so their wheels, what they are doing. So if we will see the vehicle moving, so we will say that wheels are rolling, right? Whatever that activity that wheels are performing or doing, so we call that wheels are rolling. Okay, so wheels are rolling, balls are rolling, or any cylindrical object is rolling. We are very clear what kind of movement will be considered as rolling. But in reality, if I will say, so what we have observed, that is very surface level observation. That is not precise, basically. So if you will go a little bit closer to see exactly what makes rolling motion a rolling, it means if you will go a little bit closer to see the wheel during its rolling motion, you will find it is very complicated to say what exactly is going on. Why? Because complicated, because if you will find that each particles in that wheel are doing their own motion, different motion. To figure out exactly what is going on, it becomes very complicated because lots of things are going on, right? In that particular moment. So dealing with the rolling motion directly by observing that resultant motion, it becomes very complex. The good thing is that for rolling motion, if you will see a little bit more carefully the each particle, you will figure out that whatever they are doing, that is nothing but the combination of two kinds of simple or fundamental motion. Those are rotational and translational motion, and this is very important thing. So without discussing directly the resultant movement, we can break down that motion into two separate motion. And if these two separate motion come together, so it develops a resultant motion, we call it rolling. So that two separated motion is rotational and translational. We can discuss this separately. So we can explain and we will get a simplified idea that what is going on exactly inside that. Because rotation discussion of rotational motion and translational motion is easy, right? Easy to observe, easy to explain, right or not? So rolling motion is nothing but I'm going to talk about rolling motion in terms of that two separate motion. Rolling motion is nothing but rotational motion. In short, I'm writing that, and translational motion. Right. If you will see closely to each points, you will find that they are having some resultant direction and resultant motion, but that is nothing but the combination of these two motion. Then in your mind, in some students' mind, such questions comes that how a single object at a single moment can perform two kinds of activities. So I will say, no, it's possible to perform two kinds of activities, but simultaneously, if you are going to perform two kinds of activities, so what will appear? That will appear the resultant activity, right? But those two component activities will be hidden behind that. They will merge together and make a resultant. So what appears, that will be resultant, but you can say behind that two kinds of activities are going on at the same moment. Let me show you an example with an example, then you will get a clear idea about that. I'm going to take a Hughes wheel, right? This is a Hughes wheel. Let me make it more clear. Yes, yes. Now this is a Hughes wheel. Why I'm saying Hughes? It is a there is a reason behind that. You will understand after some time. So this wheel is, let's say, rolling, right? And you are sitting over this shaft in this manner. It's not reality. It's just hypothetical scenario. So what is going on? This is the track over which this wheel is moving. The thing is that the wheel is very huge. You cannot see the top or bottom or the rightmost or leftmost corners, right? For you, pretty much it's nothing but a wall which you can see. If this wheel is rolling, and let's say I'm just talking about a spot, so what you will only observe that this spot is circulating. Practically, I'm saying if you will observe it, so you will just find, okay, this is circulating and it's very simple to see. This is circulating, moving in this way, right? Like here it is going down, here it is going down, right? So if you will see another particle that will also circulate, you will observe that this is also circulating on a different circular path, but the same common center. Now, after this observation, you will figure out that, okay, all the particles in this wall, or you can say in this wheel, all the particles are circulating. And if all the particles are circulating and the body is rigid, it means the body is rotating. So you will conclude that, okay, this whatever body is present in front of my eyes, that is rotating. Okay. Now, if you will see on the other side, this particle is going down right here. Now, if you will see on the other side, so you will find outside that sceneries or the tree, actually it is going behind, or you can say it is left behind, right? It is moving backward, you can see it. It's not true, actually. You will see and you will get the idea, okay, it is leaving behind to me. It means this shaft is moving forward. I am traveling in forward direction. You will get this kind of idea. You can say this center is moving in forward direction. You can conclude this information just by observing on the other side. You will find that, okay, this point is moving in this direction and the body is rigid. So I can say this point definitely should also move in this direction. Why? Because the separation between the two points in rigid body cannot contract or cannot extend, right? The separation between the two points will always be constant in rigid body. So if this center is moving in forward direction, so this have to move. But we have observed this particle is going down, and we have observed because this is going forward, so this will also move forward. It means this particle at the single moment, it is doing two kinds of motion, right? And if you will see from this place, you will find a result, and you will observe a resultant velocity is there. It is going in this direction, right or not? But inside this resultant, there is two particular motion hidden, right? And those two particular motions are very simple and fundamental motion. Here you can see this velocity is the tangential velocity, or you can say the velocity associated with the circular motion. And this velocity is what the translational motion, which will be exactly same as the translational motion of this center, right? Because bodies are rigid. So it have two. kinds of motion. This is translational, this is tangential, and then you will see a rate resultant speed if you will see from this, right? So I hope now you got the idea that how rolling in the rolling motion, the particles can have two kinds of motion, rotational and translational both, right or not? Now let's go in a little bit more deeper. Now, as we have seen, rolling motion is nothing but sum of two motion, rotational motion plus translational motion, right? So let's talk about a wheel here, circular wheel. I'm just imagining, and I'm drawing here two circles to show two kinds of motion. So translational motion here, if if this is center of mass, if it is moving with VCM, so I can imagine this all particles will move with the same translational speed, right? With the same center of mass speed. Yes, VCM. VCM, if you will talk about this particle, so it will also go in the forward direction with the same VCM. This is for the translational. If let's say if this wheel is rotating with omega cm, means omega angular speed around this center of mass. So we can imagine this particle is going in this direction with tangential speed, and here this particle will go in tangential with tangential speed because it is circulating, right? This is V tangential, V tangential. What about this particle? So this will be on a different circle because it will have a radius small r. Let's say I'm taking radius here as a capital R. So this will have this direction tangential speed, right? Okay. Now let's talk about the combined effect on this. So here at the center, yes, it would have only VCM. If you will talk about this point, so it will have VCM as well as V tangential. So resultant speed we will observe here. Let's talk about this point. So here V tangential and in this direction VCM. So you can clearly see the resultant speed for this is different, right or not? For this particle, it is going in this direction. If you will talk about this particle, so here it is VCM. So V tangential is in backward side. So here maybe VCM is more, so resultant velocity will come in this direction. For this, here it is VCM. So no, it's tangential. It's a tangential. So in this direction, VCM, and you can see this have a different resultant speed. And what about this particle? It will have V tangential in this direction and VCM in this direction. So resultant, it will have a different. So every particle have their own speed on direction, right or not? All the particles are moving in different way. So from that, we can conclude it's a very complex. So I will not directly study the rolling motion in this way. I will just try to separate that. And rolling motion is easy to study. Sorry, rotational motion is easy to study separately, and translational motion easy to study separately. We will got the details easily, and if we want to see ultimately a final result, how it will appear, so we will combine them together in the last, but it is not required. We can complete that whole discussion in terms of this and this separately, and we will understand all the time what is going on, right? So, so in real scenario, how it will look like if you will focus on each point. So let me draw three positions of wheel. If you will see this point, what is going on if it is rolling with omega cm and translating with vcm speed? So if you will observe this point, which is in contact with the surface, so it will go in this way. a very unique path it will follow. It's not parabola or circle. It's a different path. We call it cycloidal. Every particle will follow the same cycloidal path. So on this path, it will have a VR, means it will have two speeds, a VCM and V tangential in this direction, right? So resultant speed will be there. So if you will see properly this dot on this wheel, so what kind of path or what kind of motion it is doing? It's a completely different kind of motion, right or not? Which is sum of these two motions. So it's okay. If you will see one particle, so it's easy to see it's this path is known as cycloidal, right? But we will try to study all motion in terms of VCM and VT separately. Okay. Now let's go for the next discussion on the rolling motion. Types of rolling motion. There are two kinds of rolling motion. We call it pure rolling motion and rolling with sliding. Now, let's talk about the pure rolling motion. There are two categories, pure rolling and rolling with sliding. Here we are going to start with the discussion of pure rolling. Pure rolling means you can say in another words, rolling without sliding. What does it mean? Let's talk about a example. I'm taking a disk as a round object, right? It is placed on a rough surface, you can say. Yeah, there is a rough surface. And here, if it is moving with, rotating with the angular speed of omega cm and it is moving with translational speed vcm. So the point of contact, which is, I'm going to call it P, let's say disk have mass m and radius r. So what will happen with this point? So if it is a pure rolling or rolling without sliding, without skidding, for that this point P relative speed should be zero. Relative speed means the speed or the motion of the point P with respect to surface. I'm taking the surface sufficiently rough surface. And I'm just considering the surface is stationary or at rest, you can say. You can see the case like a platform, a moving platform, which is sliding with speed V. Here we have a round object attached with this, right? Platform is moving and round object will have VCM and here it will have omega cm, right? These velocities are with respect to ground and platform having also the speed with respect to ground. So basically relative velocity of point of contact with respect to surface, that should be equal to zero. Here the point P with respect to surface, that should be zero. It means if you will talk about speed of point P will be what? So as we have already discussed in the previous discussion, if it is translating as well as rotating, so it will have two speed VCM, omega cm. This I'm talking about with respect to ground. So net velocity, I can say VCM minus omega r omega, sorry, it is r omega cm. If radius is r, the tangential velocity will be, tangential speed will be r omega cm. Okay, this is the velocity of point P with respect to ground minus velocity of surface with respect to ground, that should be equal to zero. It means VCM minus r omega cm, that should be equal to velocity of surface, or you can say here it is nothing but V. Okay. So in this case, I'm taking the surface at rest. So simply I can say the velocity here as VCM, and here in this direction because it is rotating in a clockwise manner. So r omega cm will come backward. So here VCM minus r omega cm. Why minus? Because it is in opposite direction. I'm taking this direction as positive and backward side as a negative. So this velocity should be equal to zero because surface have zero speed. So net velocity of this point P should also be zero, which will be zero with respect to the surface. It means here VCM should be equal to r omega cm. Right. Here a different kind of case, it's a different kind of case in which the surface is also moving. We will discuss about this in a separate discussion in more detail. Let's first start with the simpler one. Right, so I'm just taking the surface here as a rest surface, right? So from this, we got the idea for relative velocity of point P with respect to surface should be zero. For that, VCM should be equal to R omega Cm in this particular case, right? Similarly, the other quantities like acceleration, if it is accelerating with ACM and it will have a rotational what you can say angular acceleration alpha Cm in this direction because rotational motion. So alpha Cm, ACM is there. So this quantity also, because all the relative motion properties should be zero here. So ACM should also be equal to R alpha Cm, right? So we can say ACM is acceleration of this translational acceleration, and this is the tangential acceleration R alpha Cm. Both should be same to make the relative acceleration of this point P with respect to surface zero. Right. So these are the key important informations. Now let's talk about the forces. So let's talk about kinetic friction. Basically, kinetic or dynamic friction will be zero. Why it will be zero? Because this point with respect to surface is at rest. This point doesn't have any relative motion. It is not sliding relative to surface. So kinetic friction cannot exist in pure rolling motion, right? Because for kinetic friction, actual relative sliding should be there. We have already studied in the friction concept. And if let's say F external, which is parallel to surface, that is also zero. F external except the friction, any external force which is parallel to the surface, if that is zero, then we can say static friction will also be zero. Means if F external parallel to surface is not there, it means no tendency of relative sliding is produced. No tendency of relative sliding, right? Here, no actual relative sliding in pure rolling, of course. If there is no tendency also, so static friction will also be absent, right? But if F external parallel to surface is not equal to zero, so except one case, there will be a tendency. What that except one case is, I will discuss later in further discussion. But here, just forget about that special case. Just try to understand if F external is not equal to zero, it means it will cause a tendency to slide parallel to surface. It will cause a tendency. Some tendency is present. Or you can say some tendency of relative sliding, simple, right? Some tendency of relative sliding is there. In that case, then static friction will not be equal to zero. Static friction will come and it will try to ensure that there should not be any relative sliding and the pure rolling will be continued, right? So static friction may come, may not be also, right? So as I have told you, there is a special case in which even external force is also acting, but after the presence of even external force, even after that also no tendency will develop. That is a special case. We will talk about that later, right? So in most of the time you will see that if F external is acting, so there will be, due to that, there will be some tendency of relative sliding and then friction, static friction will come. So basically the static friction will always come only due to the tendency, right? Tendency of relative sliding. Kinetic friction can never come because there cannot be any relative sliding because it's a pure rolling, right? So this is what the concept about the pure rolling. Now let's talk about a question. It's a for more better understanding, we have to see some question. Question is like that. There we have, let's say I'm taking disk, or you can take a sphere also, no problem. So I'm taking a disk which have mass m, radius r, so it will have some moment of inertia also. That is mr square by 2. Basically, I will use that concept, use that formula in coming calculation. Question is that there is a force which is acting in this direction. This is an external force, so it will build some tendency of relative sliding also, right? So it is asking, due to this external force, surface is first of all sufficiently rough. Sufficiently rough, I'm saying it means friction is capable enough to maintain the pure rolling. It will not allow sliding, right? Sliding of the point which is in contact with the surface. So here, in the presence of this force on this disk, it is asking what the acceleration, translational acceleration or acceleration of center of mass, and what kind of direction of friction, and how much that friction is, basically. So these are the two questions. Let's talk about that. It's a very important question to understand the concept in more detail. So first of all, acceleration and friction. If acceleration and friction will be, if acceleration or any force will be asked, so what is the way to solve this question? So we will go for the free body diagram method, in which we will take the system, we will show all the forces, and then we will try to figure out acceleration via applying the Newton's second law, right or not? So let's talk about this, because we have to calculate acceleration in horizontal direction. So I will be concerned for the forces in horizontal direction. In vertical direction, normal reaction and gravity will act, right? So basically, one force is present already, and another forces will be contact forces in the horizontal direction. So that is only the friction, we can say. Normal reaction will be in vertical direction, right? So friction, how we should show? We have a habit to show friction opposite to the external force, parallel to the surface, whatever this force is there. uh, Always we apply the friction in opposite direction. This kind of habit we have, right? So here it will be true or not, we don't know. In the last of the solution, we will see that. Let's go with the same basic understanding. One more force should act, and that force should be friction. So I have taken system, I have isolated it. Now I'm showing all the forces. So my intuition is saying friction should be in this direction. If you don't know really where it can be, so just apply that. If it will be wrong, so in the last result it will come negative in value. It will which will suggest us, okay, it's not the correct direction, right? So let's talk about, this is the forces only. Now acceleration is there, and there will be rotational effect also. So we can say there is uh, alpha cm also, right? Angular acceleration will also be there, right? So in that case, this is for me as the center, and radius is r everywhere, right? So we have to apply the Newton's second law to just find out the unknown values like acceleration or the friction. So first of all, translational Newton's second law I'm going to apply. Newton's second law. Newton's second law. So in translational Newton's second law, all the sum of forces will be equal to the mass into acceleration. So here I will take this force as positive, and the friction is acting in backward direction. That definitely it is static friction. So F minus Fr, you should say it is Fs, static friction is there, right? Fs. And these two forces sum together, it will give you mass into acceleration of center of mass, right? Now, this is the equation one for me. ACM is unknown and Fs is unknown both. Now, I can talk about rotational Newton's second law. Let's talk about this. Rotational Newton's second law. According to this, net torque will be equal to I alpha. Right. So net torque, first of all, you can see about the center of mass I am figuring out. Right. So the force F is going to provide a clockwise torque, and the friction force is also going to provide the same clockwise torque. It is going to support the force, right? So we can say F into R plus Fs into R, that is equal to I alpha Cm. Okay. Now F plus Fs R, I can take common. Here moment of inertia will be mr square by 2, of course, for the disk. ACM alpha Cm can be taken as what? Because we have an information for pure rolling, we know very well ACM of this point of contact and R alpha Cm, this tangential acceleration, both will be same. ACM and R alpha Cm will be same. So it means alpha Cm can be taken as what? ACM divided by R, right or not? So this R and this R and this R square all will cancel out. So we can say F plus Fs, that is equal to MACM divided by 2. Now this we got the equation 2. Now with the help of these two equations, we will first of all cancel out the friction and we will get the ACM. Let's talk about that. So I will add the equation 1 with equation 2. If you will add it, so 2F and friction will cancel out. So it will be equal to 2 and MACM by 2, and this is MACM. So it will be ultimately 3 MACM by 2 after addition, right or not? So now we have to figure out how much the ACM. So it would be 4F divided by 3M. We got that it is coming positive. So yeah, direction, whatever we have assumed, that is perfect. So in this direction, net acceleration is. Now time to calculate the friction. Put this equation, put the value of acceleration in the equation 1, put ACM in equation 1. So what we are going to get? F minus Fs, that is equal to M into 4F by 3M. So here M and this M will be cancelled out, and then Fs will be ultimately F, and here it will come 4F by 3. Then Fs is what? Minus F by 3 Newton. Can you see it's coming negative? Oh my God. So what do you mean by that? So basically what you have applied force here, you were thinking that okay, actually force is acting in this direction. It is causing the tendency to slide in this direction. That's why you are applying friction. But the problem is that tendency is not coming in the forward direction to slide. It's wrong. How? If force is pulling it in forward direction, so it should be dragged in the forward direction. So basically this force is not only responsible for translational motion, it is responsible for rotational motion also. It is responsible for translational force and the rotational force we call the torque, right or not? So basically it is responsible for the development of ACM as well as alpha CM also. So basically we can say here what the ACM is coming in comparison to R alpha CM, means tangential acceleration of the rotational or circular motion of this point, R alpha CM is dominating. R alpha CM is dominating, due to that relative sliding is in this direction, R alpha CM is in this direction. So we can say the friction should act in this direction to counter this relative sliding. It always acts in opposite direction of relative sliding or tendency of relative sliding. There is a tendency of relative sliding in the backward direction. I'm writing in short. So this is what the thing here concept, right? So in the case of flat surfaces, a force is acting, so rotational effect is not that much, or you can say only translational effect is there, due to that it is trying to slide in the forward direction, or tendency is developing in forward direction. That's why friction is coming in opposite. But here translational effect is also significantly present, and with the rotational effect also. And now the tendency will come in which direction, it depends on which effect is more dominating, rotational effect of this force or translational effect of this force is more dominating, right or not? So here directly just by observation we cannot say in this manner, right? So we have to be careful for that. So this is very important question to just understand the details of this, right or not? Let's talk about one more question. So as we have seen in the last question that friction is coming with negative value of f by 3. So actually it is not in this in the direction what we have assumed. It should be in forward. It will come in the support of the force to balance the translational effect, because rotational effect due to that force which is acting on the top is dominating on the translational effect. So whatever less effect of translational effect, that will be covered up by the friction if it will come in the forward direction with the force, right? So it will contribute to increase or enhance the translational effect to balance the rotational effect, and ultimately pure rolling will come into picture, right? So this is the complete phenomenon. Now let's talk about another question. I'm taking the same scenario, but force is now not acting on the top. Let's say force is acting at this place, right or not? And the same disk we have, mass m and radius r. Again, the same question, that what should be the ACM and what should be the friction, right or not? Static friction. This is the question. Again, we have to follow the similar process because, because we have to calculate again the acceleration or any force. So we have to follow the same Newton's law of motion, right on. So we have to follow the free body diagram concept. So for that, first of all, it is present on the surface which is sufficiently rough, right? So if it is sufficiently rough, force is acting in this direction. So I will first of all take a system, the wheel I'm taking as a system, the disk is system for me, and I will show all the forces. I don't know where the friction should act exactly, so I will take any direction, right? With my intuition, it feels like it should act in backward side. So if it will be wrong, so ultimately in the question result, it will show the negative sign and we will get the idea, okay, the direction was wrong. It's okay. So here we can say static friction is acting in this direction. Two forces are there in horizontal and vertical, normal reaction and gravity is also there, but I am ignoring those things because I want to calculate acceleration in horizontal direction, right or not? So here if ACM is there, and rotational effect is coming as alpha cm, right or not? So in that case, again, if it is a pure rolling, so I can say in this direction acm, and if this particle will have in opposite direction r alpha cm, this r alpha cm should be equal to acm, right or not? So alpha cm can be taken as acm by r. Okay, now let's talk about Newton's second law to figure out the ACM and friction. So if Newton's second law, translational Newton's second law, you will apply. So F minus Fs, that should be equal to mass times acceleration, right? In the direction of this F, I'm taking as a positive, or in the direction of acceleration, always I take positive direction. Opposite to that will be negative. So F minus Fs is equal to M ACM, that I will call it as equation one. Let's talk about rotational Newton's second law. So in the rotational, the torque due to the force F about the center of mass will be 0. Only friction is there to provide the torque Fs into R. Now, the I alpha cm will come. Let's rewrite or modify this expression. I will be taken as mr square by 2 because of its disk. So alpha cm will be acm divided by r. Okay, together all this r, it will cancel this r square. So ultimately we are getting Fs as MACM divided by 2. The problem is that what the Fs value depends on the ACM, which is unknown for us for now. So I will call it the equation 2. Now what we can do, we can add the equation 1 with equation 2. So Fs and this Fs will cancel out. Then F will be equal to what? 3MACM by 2, right? So this will come. Ultimately, we will get the idea about ACM. ACM is how much? 2F divided by 3M. This is our answer. So it is coming positive. So yes, the direction of acceleration is perfect. Now let's talk about the friction. So put ACM in equation, let's say 2. So Fs is what? 3m by 2 ACM if you will put, so it is 2f by 3m, right or not? So m and this, okay, everything is going to be cancelled out, right? First of all, let me check everything's fine. Let me recheck again. ACM is coming how much? If I will add this equation to FS cancel ACM, and this will give you 3m ACM by 2, so it would be 2f by 3m, of course. So now I will put the ACM value, which is 2f by 3m. So 2f by 3m, 3m is going to be cancelled out, and this 2 will be cancelled out, and FS will come exactly equal to the FS positive value. That's interesting. Why it is coming positive now? In previous case, it was coming negative. It means direction should not be that, it should be reversed in previous case. But here, this direction is perfect. Why it is happening? Because again, I told you that force, whatever it acting, that is acting at the center. So it will have translational and rotational effect. So, and you can say here the rotational effect of force is completely zero. Only what is present, the translational effect present. Due to this translational effect, this ACM will dominate, right? This ACM, translational acceleration, will dominate on the R alpha CM. So automatically what will happen? Automatically ACM will dominate. So net relative sliding tendency will come in the forward direction. So friction will come into picture to fill the gap of R alpha CM, whatever it is less in comparison to ACM. It will friction will try to enhance the value of R alpha CM so that it will become equal to the ACM and it will maintain the pure rolling condition, right or not? So relative sliding will be restricted by this FS because tendency has developed because of domination of ACM. Why ACM is dominating? Because force is contributing more in translational effect, right or not? Or you can say rotational effect is completely zero here because torque is about the center of mass due to force is zero here, right? So we got the idea. We have seen in the last question that force was on the top. So it was showing more rotational effect in comparison to translational effect. At the center, exactly, translational effect becomes dominating. It means from center to top, if you will move. So translational effect will be there, but rotational effect will increase due to the force, right? And as much as it will go at the away from the center, rotational effect will be more and more. And after some time, you will find that rotational effect becomes more greater than the translational effect of the force. In that case, friction has to change its direction because relative sliding tendency will come backside as we have seen in the previous case. So it means there will be a transition level, means from the center as you are going away from the center to apply a force. So there will be a position at which if you will apply the force, then the translational effect and rotational effect will be exactly same. They will cancel out. There will be no domination of translational on the rotational, or there will be no domination of the translational rotational on the translational. Just try to listen me carefully. So it means by the force itself, whatever it is providing translational effect, the same rotational effect is also coming. They are canceling by themselves only. There is no relative sliding tendency. At this situation, there is no requirement of friction, right? So this we will discuss in more detail with the example properly. Then you will be able to understand. So this kind of discussion we will do in the next time. So I hope you have understood and you have enjoyed the complete discussion. We will meet again. Thank you. Bye bye.